So, now we've discussed all the constraints on the condition definition process, let's now think about how the modular hierarchy can develop and change. First, I need to establish the concept of similar conditions. So, suppose this represents an array of visual detectors, each small squares a pixel. Then suppose that different visual images are focused on the array. But to get the concept of similarity, let's just simplify the image by eliminating the color, and also let's say a pixel is just either on or off. Those black dots could define a simple condition, a specific group of pixels, with the condition being detected if all the pixels are illuminated, as they are in this image. At the bottom, two similar conditions are illustrated. They're similar because their definitions overlap significantly. The pixels circled in green on the left image are also part of the definition of the condition on the right. There's just a couple of pixels difference between the conditions. So they share quite a high proportion of their pixels. And they're also similar in the sense that they've been detected at the same time. In other words, they're present in the same image. These two similarity factors both suggest that the two conditions are likely to have similar behavioral implications. They may be appropriate for recommending similar behaviors, like naming the same object in this case. Now let's suppose that there's an array of modules, say columns, but representing those columns by the pot of conditions model. And we'll use this to look at how receptive fields could change. Let's suppose there's already been some learning. So each module has already defined a set of conditions. And suppose that in this conceptual array, at least two receptive fields must be detected in every input state. Remember, that kind of minimum limit is to make sure there's a sufficiently extensive range of recommendations in response to every input. And let's suppose that if 4 or more conditions are detected in one module, the receptive field of the module will be detected. So if you like, that's the threshold for receptive field detection. So if you see a familiar type of bird, there's enough condition detections indicated by red to reach the minimum number of receptive field detections. If you see a less typical type of bird, there's fewer condition detections and only one receptive field is detected. But in column E in this case, it's not being detected, but there's quite a lot of condition detections, and one more will be sufficient for receptive field detection. So a new condition that's actually present in the current image is added to module E. In other words, there's condition recording. Module E detects its receptive field. Now there's two modules generating an output, and there'll be no more condition recording. If it's an even more novel bird, the number of conditions may be even smaller, and you might not get any receptive field detections initially. But there's a couple of modules, B and G in this case, that have rather more condition detections than the others. So conditions that are actually present in the current image are added to each of these modules, and you get two receptive field detections. Now, let's step back and think about array receptive field detections on a slightly higher level of description. Suppose that this is an array of columns that's defined receptive fields in a wide range of different visual objects. The modules coloured red in this array are those that have sometimes been detected within different visual experiences of birds. Now, only a few of these columns will detect their receptive fields in response to any one bird experience, and it'll be a different few in each experience. And none of those red columns will be activated in response to all bird instances. But all the red columns will have a bit of recommendation strength in favour of bird-appropriate behaviours, like saying that's a bird. And the recommendation strengths will be roughly proportional to the frequency with which the module is being detected in different bird instances. So in response to that specific bird instance, the illustrated subset might be activated. A different bird experience, a different subset. Another bird, another subset, and so on. Now, suppose that a novel type of bird is perceived visually. And suppose also that in this array, the minimum number of columns that must be detecting their receptive fields is 5 or 6. Because it's a novel type of bird, maybe only a couple of columns active in the past when other birds were seen are immediately activated. Perhaps also a column that's never previously been activated in response to birds, but maybe sometimes activated in response to fish, for example. But even together, the total number of columns activated is below the minimum, because the novel object isn't sufficiently similar to either a bird or a fish or anything else. So there's going to be receptive field expansions to increase the number of activated columns. And I've indicated the presence of expansion by red that gets a bit darker towards the bottom of the column. Some of those expansions will be by modules that have responded earlier to other bird experiences, so they'll have some bird-appropriate recommendation strengths, again like saying that's a bird. Other expansions could be by modules that never responded to birds before, only to other types of objects. So at the end of the expansion process, a fair number of active modules could have existing recommendation strengths in favour of bird-appropriate behaviours. So there's a reasonable chance that a bird-appropriate behaviour will be selected. If the selection is rewarded, even the previously non-bird modules will get a little bit of recommendation strength in favour of bird-appropriate behaviours, increasing the chance of an appropriate response to similar objects in the future. And of course, if the wrong response is given and there's negative feedback, recommendation strengths in favour of the incorrect response will be decreased, reducing the chance of an incorrect response in the future. And we'll discuss later how imitation of a teacher, for example, can make the learning process for recommendation weights even more effective. But remember, the reward feedback isn't changing the receptive field definitions. If a receptive field is detected, one of the recommendation weights associated with it may change. So going back a moment, the red columns are those that sometimes respond to instances of birds. But the same array must also be able to identify other types of visual objects, like cats. And there'll be a range of columns that sometimes detect their receptive fields in response to cats. Again, not all of them in response to any one cat, a different subset each time. All these columns will have some recommendation strengths in favour of cat-appropriate behaviours, like saying that's a cat. Because there could be some visual similarities even between birds and cats, they both have heads, 2 eyes, legs, etc., there could be some modules that detect their receptive fields in some instances of cats and some instances of birds. These modules would have recommendation strengths in favour of both cat and bird appropriate behaviours. But for any specific instance of cat, the predominant recommendation strength across all the detected receptive fields needs to be in favour of, for example, saying that's a cat. And similarly, for any specific instance of bird, the predominant recommendation strength needs to be in favour of saying that's a bird. So the key requirement is to ensure that columns can provide adequate discrimination between input states with different behavioural implications. In other words, all the different groups of modules activated in response to different birds must be sufficiently similar to each other and sufficiently different from all the groups activated in response to cats that it's possible to assign combinations of recommendation strength to each receptive field in such a way that high integrity identifications for every instance of all the different categories is possible. But what if there's a problem? What if the discrimination isn't adequate? Think about the columns activated in response to cats and the columns activated in response to different dogs. There's more visual similarity between these types of visual objects and probably more overlap in the columns. Suppose that the system sees this dog, and some set of receptive fields is detected, and the predominant recommendation strength is in favour of saying that's a dog. Then there could be positive feedback, for example, from a teacher. But now suppose that the system has a visual experience of a cat, and because of the visual similarity, pretty much the same set of columns is activated. The behaviour will be the same, saying that's a dog, but the teacher feedback will be negative. So with the same columns, resulting in the same behaviour, the feedback is sometimes positive and sometimes negative. Now how can the system resolve this problem using only the information it can plausibly have available? Well, the activation of the same group of columns, followed by the same behaviour, resulting sometimes in positive and sometimes negative feedback, is an information condition which the system could detect via some kind of receptive field. Detection of that kind of receptive field could result in the group of modules acquiring recommendation strengths in favour of extra receptive field expansions whenever the group is detected again. So there'll be additional modules activated by receptive field expansions in response to similar future instances, even if they aren't needed to meet the minimum numbers. And eventually, additional columns will provide discrimination between the similar but different category objects. Modules like columns don't correspond with cognitive categories. So what do they correspond with? I've got an example from a different domain that perhaps will provide a bit of a feel for what they're like. Suppose you have a database of face images. To do face recognition by machine, one technique is to take that set and process the image data to create a set of secondary images that don't overlap in some mathematical sense. We call these images eigenfaces, and they capture the differences between the images in the original set, with the earlier eigenfaces capturing the larger differences and the later eigenimages capturing smaller differences. Then you pick the images that carry information about the largest differences, and then to identify a face, you measure the degree to which each of these eigenfaces is present in that face. And because the eigenfaces are present to different degrees in different faces, the mix can be used to link a name to the face image, much like assigning recommendation strengths to receptive fields. But in this case, the receptive fields are actually the mathematically defined eigenfaces. And you can create sets of face images by a number of different mathematical approaches, including calculating images that have the maximum degree of statistical independence. And these types of what I call pseudo-face images can also be used in the same way for identification of faces. Like the receptive fields I've been discussing, the images individually don't correspond with individual identities. You have to use the mix of different eigenfaces present in a face to identify it. So to a degree, you can imagine receptive fields as looking a bit like this. But having said that, there are some important differences. The key difference is that the principal and independent components are calculated in advance from a set of reference images. They don't change gradually with experience, and that limits their ability to cope with novel images. Because of the way they're defined, receptive fields are relatively, but not precisely, independent in a statistical sense. Mathematical and statistical components are calculated for a particular set of faces. You'll always get the same set of eigenfaces from the same set of faces, while receptive fields will differ depending on the order in which the faces are experienced. But the biggest difference is that the components have to be calculated in advance for the complete set of faces. Receptive fields, on the other hand, evolve smoothly over time. If lots of new faces need to be recognized, the eigenfaces will have to be completely recalculated, invalidating all the previously assigned weights in favor of different identities. So although these components can give you a feel for how receptive fields look, the component approach wouldn't work for a system that had to heuristically define a complex combination of behaviors.